Hey everybody, so we are going to spend a little bit of time reviewing a couple of problems, or at least one problem for this video. And what we're going to do is we're going to look at Brown, LeMay, and Burston, and we're going to look at question number 33 right here, okay, where we have a reaction between hypochlorite, OCl-, and iodide ion, okay? And so what we want to do is we want to find kind of the standard things that we would find in every sort of reaction. We want to find the rate law, we want to calculate the rate constant, and we want to calculate it when we want to calculate the rate when we've reached some, or when we have some sort of given concentrations. Okay, so I've set this problem up already, so we can go from here right to here. So this is the problem. Okay, so if we are going to write the rate law, okay, now the rate law is in the form R rate equals K times the concentration of the reactants, OCl minus, to some power M, times the concentration of the other reactant to some power N. Now, if there was 17 reactants, we would have to write 17 of these different things down here, okay? But this is the way it works, okay? So, here's what we're going to do. Okay, in order to find the M and the N, we have to determine the order by comparing rates. So what I'm going to do is I'm going to label, just to make this a little easier, I'm going to label this experiment 1, experiment 2, and experiment 3. Okay, that just allows me and you to get on the kind of the same page. Now, I'm going to go through this super slow so that you kind of know what the heck is going on. Okay. In order to solve this problem, we need to use something that we call the method of initial rates. And that allows us to compare the experiments, like the experiments between the experiments of 1 and 2 to each other, okay? And by doing that, that shows us the change in the rate, okay? So chemically speaking, the rate is changing, and how is the rate changing? Well, it's not changing because the concentration of I is changing, chemically speaking. This is staying the same. So what's happening? The rate here is changing, or sorry, the concentration here is changing. So that means the rate here. So that's where the rate is changing. Okay. So what this means, what we're going to do is we're going to take some time and we're going to compare rate 2 versus rate 1. Okay, which equals rate 2 is 2.72 times 10 to the minus 4 over 1.36 times 10 to the minus 4. That equals, well, K times the concentration of OCl minus raised to the power M times I minus raised to the power of M. That's for rate 2. Now for rate 1, it's the same thing. K equals the concentration of OCl minus raised to the M times the concentration of I minus raised to the N. Okay? This form will always get you to the correct answer. Okay? But we can now cancel some things out. Okay? What I mean by this form will always get you the right answer. If we write all of this out, okay, if we get stuck, like let's say something isn't working up here, always go back to this, like the most expanded form before you cancel anything out. Because what we know is K is going to stay the same. So the K's cancel out. Now we picked experiments 1 and 2 because look at the concentrations. The concentrations of I minus stay the same. So this over this is going to cancel out as well. So what we have is that this R2 over R1 equals the concentration of OCl minus raised to the M power for 1 over the concentration of OCl minus to the n power for experiment 1. So this is experiment 2 and this is experiment 1. So now let me pull up my calculator. So we'll take a look at this. So what is 2.72 times 10 to the minus 4 divided by 1.36 times 10 to the minus 4? And so this is 2, okay, 2 equals, and then what is the concentration here? 3 times 10 to the minus 3, 3.0 times 10 to the minus 3 over 1.5 times 10 to the minus 3. That's the concentration of OCl in experiment 2. This is the concentration of OCl in experiment 1. And all of that, because it's the same power, is raised to the power of m. So what is 3.0 times 10 to the minus 3 divided by 1.5 times 10 to the minus 3, and that's equal to 2. So you get that equals 2 raised to some power m. So 2 equals 2 to the n. And that is going to, so in this case, m equals 1. Okay? Now that gives us one of the orders. Now we have to calculate the second order, the other order. Okay? And so we're going to pick the experiments where we're holding, instead of I minus constant, we're going to pick the experiments that OCl minus is being held constant, which is experiments 1 and 3. And so again, we're going to look at this, we're going to look at this rate, we're going to compare green, and I always want it to be a whole number, so I always pick the bigger one and put it over the smaller one. So this one, for OCl minus, for hypochlorite, is going to be rate 3 over rate 1 equals, let's see, okay, so rate 3 is 2.72 times 10 to the minus 4, 2.72 times 10 to the minus 4 over 1.36 times 10 to the minus 4, and that equals, again, K times the concentration of OCl minus raised to some power, let's see, m, or sorry, it's not even m. We know what power that's raised to. It's raised to the first times the concentration of iodide ion raised to some power n. And then we do the same thing on the bottom. K OCl minus raised to the power of 1 times I minus raised to the power of n. Now again, if you get stuck, if something doesn't look right, then we have to always kind of go back here. I don't cancel things out unless I absolutely know that it's going to kind of work out, that there's experiments where everything that you can cancel out. Okay? So, again, K is the same. OCl minus is the same. So that means that now we get that that is equal to I minus to the n over I minus to the n. And this is for experiment 3, and this is for experiment 1. Now, I will say that you can probably do this math in your head. I would hope that you could do this math in your head. Okay? If not, we've already done this math on our calculator up here. If we look, you can see 2.72 times 10 to the minus 4 divided by 1.36 times 10 to the minus 4. That is equal to 2 still. And then the concentration of I minus is 3 times 10 to the minus 3 for experiment 3, divided by 1.5 times 10 to the minus 3. So it's 3.0 times 10 to the minus 3 over, 1.5 times 10 to the minus 3. And all of that is raised to the n power. So what is 1.5, or 3.0 divided by 1.5? Again, that's right there. And so we get 2 equals 2 to the n. So that means that n equals 2. or sorry, n equals 1. See, and this is how silly mistakes happen. I just saw a whole bunch of 2's and I just wrote a 2. So the rate law for this equation, we still haven't answered the question. The rate law, R equals K OCL minus to the first times I minus to the first. So this is the rate law. Okay, you have to show the powers in there. Okay, now I get it, you don't have to put the 1, but I always want to show the 1 because I've done all this work, so it makes more sense to kind of put the 1 in there. Okay, now what's the second part? The second part is calculate the rate constant for proper using and including proper units. So now that we have this guy right here, we can substitute in any of these values, either experiment 1, experiment 2, or experiment 3, as long as we use the same experiment for the rate, the concentration, and the concentration. Okay, we can't choose this, this, and this. We have to choose this, this, this to do this. Okay, so I am going to pick experiment 3. Why am I going to pick experiment 3? I don't know. It'll work for any of them. It doesn't matter which one you pick. I pick experiment 3 because I always feel like when people do these problems, experiment 1 is kind of is always picked, and then experiment 2, maybe people experiment 2. Nobody ever picks experiment 3. It's stuck there all kind of by itself. So all I'm going to do this, to find what the rate constant is I'm going to substitute in, let's see, the rate was 2.72 times 10 to the minus 4 equals K, which we don't know. Let me take this and move this guy down a little bit. Okay, times the concentration of OCL, which was 1.5 times 10 to the minus 3. So this is times 1.5 times 10 to the minus 3, and that's raised to the first power, times the concentration of I minus. The concentration of I minus is 3 times 10 to the minus 3. So this is 3 times 10 to the minus 3 raised to the first power. Okay, so now it's time to do a little math. Okay, we want to solve for K. So we're going to take 2.72 times 10 to the minus 4 divided by 1.5 times 10 to the minus 3. Okay, and so that divided over here, and then we're going to divide by 3 times 10 to the minus 3, divided by 3 times 10 to the minus 3. Okay, so we get K equals, isn't that funny? K equals 60.44. But now it's asking for a unit. Okay, well, in order to figure out the unit, we have to go up here and notice this is molar per second. Okay, so that's fine. Molar per second. Okay, so to find the unit now, what we can do is we can use the rate law, R equals K times the concentration of OCL minus to the first times the concentration of I minus to the first. We can use that rate law and we can plug in the units. Okay, so molarity, molar per second, that is the same as saying a mole per liter second. Okay, and that equals, well, we're looking for the unit of K. What's the unit of concentration? Mole per liter. And what do we raise that power? We raise it to 1. And now we have another unit of concentration, moles per liter. We raise that to the power of 1. Okay. Now, so mole per, let me go up even further. Mole per liter second equals K. Now we're going to combine this. Mole squared, let's see, liter squared. So in order to get this side to look like this side, we have to come up with units of K that cancel and add the units to make it look like this. Okay, so we have 2 moles on this side. So what we want to do is we want to get rid of 1 mole here. So now mole will cancel, and one of the moles will cancel, leaving 1 mole. So now that looks like this side. We want to get rid of 1 liter. Okay, so liter, and then one of the 2 liters cancels out. So now that works. And now we're going to put a times second there, because when you multiply by seconds, it's going to be that. So now that's our unit. So our true answer here is going to be 60.44 liter per mole second. Okay? Now there's one last part to this problem here. It says calculate the rate when the concentration is 2 times 10 to the third and 5 times 10 to the fifth. Well, now that we have this, we can calculate it at whatever concentrations we have. Okay, so for part C, we have rate equals K, the concentration of OCl minus to the first, I minus to the first. And so now the rate is the thing we're trying to calculate. So we get K, which we know is 60.44, times the concentration of hypochlorite, which in the problem is 2 times 10 to the minus 3, to 2 times 10 to the minus 3, okay, raised to the first, times the concentration of iodide. The iodide concentration is 5 times 10 to the minus 4, okay, so that's 5 times 10 to the minus 4 raised to the first. And so now we can just do math. So 60.44 times 2 times 10 to the negative 3 times 5 times 10 to the negative 4. And so when we do that, we get the rate equals 6.044 times 10 to the minus 5. And what's the unit on that? Moles per liter second. Okay, so there is one method of initial rates problem. Problem 14.33.